Hi everyone, welcome to the 14th Solar Climate Intervention Virtual Symposium. So these are monthly seminars that I co-host with Simone Tilms, who's not here today. And yeah, basically, if you're interested in sharing your science around SRM, then please reach out to me or Simone Tilms, and we'd gladly have you present. So our first speaker today is Dr. Lili Xia. So Lili is an assistant research professor at Rutgers University, and her research focuses on how sudden changes in radiation affect the climate. So that includes SRM and nuclear winters. So Lili, please take it away.
Thank you, Matthew. So today I'm going to talk about agriculture responses to SRM and more broader impacts. So I will like more like telling a story instead of telling details of the research. So I think, I don't know, probably most of you will recognize this photo, this picture. Yes, this is the first geomap. That was in year 2011. I was a first year graduate student, just joined with Dr. Alan Robach's group. And in that meeting, my talk, the title is Impacts of Stratospheric Sulfate Geoengineering on Food Supply in China. So that was like the first time I started to talk about my research on impact from SRM. And then after that, I continues the work. And also I want to mention, it's almost the same time in the year 2010, that's the initiative of AgMap, Agriculture Modeling Intercomparison Project. They started the initiative and trying to bring all the agriculture modeling groups together. And this figure was shown by their leader, Cynthia Rosenzweig and AGU that year. And that's the structure they really wants to build for the whole AgMap, including data tools, infrastructure, like the whole data platform to supply to crop modeling groups to study climate impact on agriculture. And let's see how many studies have been done since then in terms of agriculture impact in this field. So the first study published in year 2012, this is a very nice study based on, they build up a statistic model based on 2 climate model output. And the scenario they use is using injecting SO2 to balance the two times CO2 world. They look at like the globally maize, rice, and wheat production change. And comparing to current climate and the reference case, which is 2 times CO2, they find out in both situations, the crop production, crop yields increased. And then in 4th years of my PhD study, I published the first paper on how SRM will impact agriculture in China. At that time, GeoMap, the first phase of GeoMap, have finished a couple of simulations from G1 to G4, and I choose G2 scenario, which is the reference case is 1% CO2 increasing, and then to reduce the solar constant to balance this radiative forcing. Because that's the scenario has the most climate model. I used 10 climate models and using the crop model DSAT to simulate how this impacts China's agriculture in terms of rice and maize. What I find is a very mixed response for rice. This kind of G2 geoengineering will very mildly reduce the rice yield, but significantly increase the maize production in China. And then the next year, another study using a different crop model looked at a totally different scenario. It's a marine cloud brightening scenario, and just focusing over China and Africa, look at wheat and groundnut. And they find out both both crops in both regions. They are not directly looking at the yield, the crop yield change, but they looked at the frequency of the failure of agriculture. So they both find the decreased failure frequency under geoengineering scenario. And then for the next couple of years, a group, they use the same agriculture model. They choose G3 as the scenario, but they only use one climate model from Beijing Normal University and look at in India how the groundnut production will change. I put those two publications here at the same time because it's pretty much the same work, but they published it twice. Even I pointed out to the editor, but still they published it. So they find out the groundnut production in India comparing with a global warming scenario without geoengineering, the yield decreased, but comparing with the current climate, it increased. And then Proctor in 2018 published a wonderful paper on Nature based on the historic record from volcano eruption. He built up a statistic model and then used one climate model simulation for the scenario of SO2 injection to balance the radiative forcing to RCP 8.5 to RCP 4.5. And what he found out is the combination, it's a combination effect from different climate changes. The effort, the benefit from cooling effect basically is balanced out by the reduction of solar radiation. So there's, if you count them together, then there's very mild change. So I just write no change there in the comparison. And then the next year, another group, they use a different crop model and look at G4 scenario, which include 6 different climate models. Still, they focus over China and look at the rice production change. And what they find is the rice production increased under G4 scenario comparing with RCP 8.5, RCP 4.5, I think. And in the year 2021, Fan and his group, they find out they use a new crop model, COM5 crop, which is right now coupled in CESM2. And they use one climate model output from Norwegians, and they used 3 different SRM scenarios, including sulfate aerosol injection, marine cloud brightening, and Theris cloud thinning. So they tested all 3 scenarios using COM5 crop offline, and then they find out for all the scenarios, the crop yield increased comparing with the reference case and the current climate. And last year, our group, the graduate student Brandon, he published a paper on nature food, and instead of looking like 1 or 2 scenarios of geoengineering, he looked at 8 different SAI scenarios, but still just looking at one crop model output since this COM5 crop is coupled with CSM. So we take the advantage just using the output from CSM2 when this model simulating all 8 different SAI scenarios, it will directly output the agriculture production. And we looked at for those 4 main crops, what's the production change under those 8 scenarios. And we still find a very mixed response. Basically over tropical region, it's geoengineering will have like a positive feedback, but it's over high latitude regions, those nations prefer global warming or very mild SAI strategies. So here I'm showing the table. If you just look at the first 2 lines, those are the conclusion. If it's green, then it's positive. If it's red, then it's negative response. So it seems like you can get some conclusion geoengineering is good for agriculture because for most of the study, it increased the crop yield. But if you look at all those details, those studies, they are using different crop models. They use different scenarios, and for different scenarios, different number of climate models did the simulation, and also for different regions and different crops. So for me, I feel we are still really far from reaching a robust conclusion on the impact of SRM on agriculture. So that's like the story I really want to share, why we are still far away from this target. But how are we going to achieve a robust assessment of SRM impact on agriculture, or even like a broader impact assessment, not just agriculture? So I want to talk about what are those uncertainties coming from. For me, I think the uncertainties are from the scenarios, SRM scenarios, and then the climate models and the crop models. Those are very broad and blur concept. And if we break it down, I feel there are two levels of challenges here. The first one I really want to, for me, I'm really trying to think about, are we making full use of current platform and tools? That means, are we really looking at all the existing SRM scenarios? So some scenarios, they have the very high global warming reference case, like SSP 58.5, and some said, okay, we'll choose a more realistic one. It's SSP 24.5. But those are different. We have different global warming paths. And also we have different design of SRM. We could cool those global for different temperature levels. And we could have different injection strategies. Are we really looking at all the existing simulations? No, we are not. So Brandon's work last year looked at all 8 different scenarios. This could be a good start, but it's still far away from enough. So he looked at for 2 different global warming scenarios, and then with different level of cooling. And then to analyze how the agriculture will respond to a range of SRM. I think that's essential, very important to really have this impact assessment with a range of different SRM strategies instead of just focusing one SRM scenario that cannot just present the whole SRM research. And then the second one, we are just using one crop model, most of the study, no, all the studies I showed before. And there are like more than 10, 20 different crop models. Can we use different crop model to simulate the same SRM scenario and then to find out how the crop models respond differently to the same climate forcing? So Brandon has a paper submitted to Earth's Future, and right now is under revision. He just tested 2 different crop models with one scenario. That's we're using a rise simulation with a temperature target 1.5 degrees Celsius. And here you can see it has really diverse response. The model we use, COM crop has a positive feedback here, but the one in the middle, it has it's almost no change for both global warming and SAI. And the PDSAT, the model I used before to conduct a study over China, it has negative impact under global warming, and then geoengineering can reduce this reduction significantly. So those models are so different when they are forced by the same climate forcing. We really need to incorporate more crop models and understand how they respond differently and why they respond differently, and then to have a better conclusion on the agriculture impact under SRM. And also there are something else we need to think about. We have crop models, but we also have agriculture index. Those are derived from temperature and precipitation, trying to predict how the agriculture, like the planting window or the harvesting window or the growing season. And Nina just submitted a work to Earth's Future looking at those agriculture-related indices over India. So maybe we should expand this to global wise and trying to understand without crop model, without the uncertainties from crop model, how those agriculture indices change under SRM scenario and a global warming scenario. And also Nina and Jyoti, they are leading another projects looking at models like simulating high value crops. Those models are already there. So I count those as existing tools we already have. It's just those modeling groups, they are not exposed to the SRM research area yet. So Jyoti and Nina, they really reached out to those groups and trying to take their model to simulate how SRM will impact coffee, grapes, wine, and cocoa and other nuts. So I think those are, we really need to think about what are the current platform existing there and the tools existing there, and really to collaborate with them and trying to have a better understanding on SRM impact on agriculture. And if we bring all those together, my question is, can we really build a platform using those existing data and tools? I actually asked ChatGPT, can you draw me a website design if we want to build up this platform? So I just give the name, it's AgMap SRM. So I hope if we have, we're trying to looking for funding to fund this kind of work to build a platform and provide different level of SRM scenarios there. And we can provide the different bias correction and the downscaling method. And then the final product will be the last part for the impact groups, the agriculture modeling groups. They will be able to choose their region. Maybe they just interested in some country, maybe in Japan, maybe in Malaysia, they are not interested in global data and they just want to look at 10 years simulation and then choose the variables they are interested. So that will save a lot of troubles for the agriculture modeling groups. And then in that way, we can invite more agriculture modeling groups or impact groups to join this kind of research. And then the second, I talked about there are two levels of challenges we are facing. The first one is whether we are using full use of the existing tools and the platform. And the second one is, can we really trust the current tool to assessing SRM impacts? So that's a question because most of the models designed to study global warming, and most of the model probably cannot really estimate SRM environment, which the CO2 concentration and the temperature is fully decoupled. So there's some work our group is doing. I'm not going to really talk details of the research, but just listed here, we're trying to develop the COM5 crop. Sam Rubin really put the prescribed crop calendar in the model to be able to compare with other crop models in AgMap. And Jyoti Singh developed the ozone damage function and trying to simulate how surface ozone change under SRM will impact agriculture. And also she included winter weight in CLM5 crop, which was not included, only spring weight was there before. And also there are other important questions. Can the crop model really respond correctly to extreme events? This is a submitted work I am co-authored with to Nature Food. I just give two examples. The first one is rice and maize. The first, if you look at the x-axis, that's the observation. That's an observation to showing how rice production and maize production responds to heat wave, extreme cold, extreme rainfall, and drought. And then after all those names are the crop models. You will see for maize, probably the model and the list simulate the direction of the response correctly. But for rice, a lot of model even respond the direction wrong to the extreme events. So we really need to think about how are we going to develop the model to better understand the impact from SRM, and as well as climate change. So I want to just expand the talk a little bit. It's not just for agriculture. This is also for ecosystem impacts and human health impacts or other impacts. I put this image here. That was the first, as far as I know, maybe I'm wrong, but I'm just telling the story from my side. As far as I know, the first symposium on ecosystem impacts of geoengineering. That was still my first year of PhD. I was there as a note taker. And from this one, they published a paper about the ecosystem impacts of geoengineering, a review of developing a science plan. And that paper very detailed described what kind of science plan we need to really understand ecosystem impacts of geoengineering. And after that, Phoebe and Jessica, they both wonderfully lead the team, Climate Intervention Biology Working Group. And we published a paper on PNIS. It's a review paper on ecosystem impacts from climate intervention. But still, after that, there's not much going on. We're trying very hard, but we don't really find a place for funding source or a platform to really help to have a full impact assessment of SRM. Recently, I will end my talk here, and I want just bring more questions to the discussion. Recently, I joined a NSF workshop. It was talking about the ethical and societal problems of SRM. Seems like NSF trying to build a program to understand the society from the social science part to understand the social science problems of SRM. When talking with the social scientists, and we find there's a big gap there. So between the natural physical scientists and the social scientists, we don't have really a full assessment of impact assessment of SRM, which would be fundamental for social scientists to really understand their question. So I want to end my talk here and open the discussion later. How can we move forward to really have an impact assessment under SRM? Thank you.
Thank you, Lily. That was great. Does anyone have questions? Andrew, your hand's up.
Yeah, I'm just curious to try and work out whether we're measuring the right thing. So, for example, if I'm a farmer, I know I have a 2% reduction in my yield in 30 years' time. That's probably unnoticeable to me and within the measurable and interannual variability of my crops, right? But if I have a year with a complete harvest failure, or I don't get anything or almost nothing out of my farm, that's devastating. So in a similar way, I mean, Alice, I don't know if she's on the call, but Alice cited something which I've colloquially referred to as the British Weather Moaning Index, which is like a really complex series of about 50 variables of things people really care about climate rather than surface temperature, which they don't really notice or care about. And I'm just wondering if these crop models are or could be optimized to look at kind of harm and damage as opposed to just crude yield output, which isn't necessarily the best driver of misery, suffering, and war.
Could you repeat the question? You said the crop model can they look at damage and what instead of yield, right?
Well, what I'm saying is like you can look at yield and you could like have the average annual yield over say a decadal period, which gives you a good approximation of what agricultural output is going to be. But it doesn't necessarily show you that, for example, in a particular region of a country, you might have a total harvest failure, right? And those kind of things.
Absolutely right. That's why I said even based on, we don't have much research going on, and based on the table I presented, we are really far away from a conclusion. It's most of the model are global models, and there are a couple looked at over the region, just certain countries. But for different places, we really need to have the model, their local researchers using the regional crop model to look at how SRM with different range of SRM, how that will impact their local agriculture.
Greg?
Thank you for the talk. It's very interesting. I'm still pretty ignorant of the modeling process and everything, unfortunately. I'm just wondering, I'm aware that there's the models which are extremely expensive, physics, et cetera, to do the modeling. And then there are emulators, which crudely I regard as interpolators on the output of the models. Are you using emulators? Do I take that correctly or not? Or are you using full-up numerical simulations?
You mean the crop model or the climate model?
Well, everything. Do you like, I mean, do you take as your data from which to
All the studies I mentioned take the Earth system model, numerical climate model, simulate different scenarios of SRM. And then the crop model I mentioned are also numerical process-based crop model. It's not an emulator. But I agree with you, there's another area of research using emulator to simulate different design of SRM, and also for agriculture modeling, they are also using emulators trying to really in terms of relative fast way to simulate a different response.
So you are therefore limited to the particular choices that the original model, or I don't know, maybe you do run the numerical simulations yourself, but you're using the exact scenarios. You have no capacity in your approach to try to estimate any other choices in the modeling, in the parameters of the model in terms of the amount of the SRM, how it's distributed, et cetera, like that. That's you take whatever models have been done and you choose one and then combine that with your own study. Is that right?
That's right. For all the impact studies, like most of the impact model, they run offline. That means they will take the climate model output and using those climate forcing to drive their impact model. But in another way, it's incorrect because if the emulator to simulate a different level of SRM can provide us the climate forcing, then all the impact model can also take that climate forcing to run their impact model using the emulator output of SRM.
All right, thank you very much.
Mm-hmm.
Okay, we have one last question from Hongwei. I think he's referring to that slides where you force different crop models with the same climate forcing, get very different results. So the question is, in the existing crop models, what processes and parameterizations cause high model uncertainties regarding evaluating SAI's influences on crop?
I think that one is those three models, they have really different response to temperature. So
okay,
that's probably the reason, and more research really needed to really understand. And also I think for me, it's also like those models have different sensitivity to CO2 fertilization effect to temperature, and then combine those together, then it has a totally different results.
Okay, thank you very much. I think we'll move on to Pat. So thank you very much, Lili. That was a really interesting talk. Pat, do you want to share your slides? Whilst you're doing that, I will introduce you. So Dr. Patrick Keyes is an assistant professor in the Department of Atmospheric Science at Colorado State University. His research focuses broadly on climate and societal change, with an emphasis on designing tools for understanding how these changes may unfold in the coming decades. So Pat, take it away.
Okay, thanks a lot. Can you hear me okay? Is it?
Yep.
Yep, okay. So today I'm going to talk about a set of research that myself and some colleagues at Colorado State CSU have been doing for, I don't know, the last 4 or 5 years or so, maybe 4 years. And it's all, and hold on, and these are some of the primary folks. So Libby Barnes at the top, Jim Hurl, and then a postdoc that's been working closely with us on some of this work, Chunrei Diao, and then Dr. Curtis Bell, who's a faculty member at the U.S. Naval War College. And what I'm going to be presenting is a series of work that's really trying to figure out how can we think about scenario design for deployment scenarios of SAI specifically that reflect social, political heterogeneity, and then trying to incorporate that as best we can into the way we think about geophysical simulations and really putting those two things together. And so probably many, I'm not sure, maybe most of you on this call today have maybe come across the ARISE SAI simulations. And this is a set of an ensemble of 10 different simulations that are trying to hold global temperatures under the SSP 245 scenario to a 1.5 degree Celsius, roughly constant at that. And on the left hand, so the top figure, if I do this, can you see my cursor? All right. So we see kind of marching forward in time that the ARISE SAI simulations hold temperature pretty well in terms of the average of the ensemble out kind of into the future at around that 1.5 degree target, give or take. And that the prior to deployment of SAI, in the decades leading up to deployment in 2035, we see that most of the terrestrial surface on the planet is warming, and that following deployment for the decades after that, temperatures are being held mostly constant. And this is again the ensemble mean, so an average of 10 different ensemble members. But this is something where I would say some of the emphasis at CSU is really on trying to understand and disentangle the role of internal climate variability and how we might understand and perceive changes in global temperature. So on the bottom now, what we see is this is an individual ensemble member in the decade prior to deployment, and the relative warming or cooling, blue being cooling temperatures over that decade and red being warming. And then this figure over here is the decade after deployment. The point being is that there's large regions of cooling and warming both before and after deployment. And that's not to say that in the long term, this sort of deployment wouldn't be effective. It's just that over the shorter timescales, over decadal timescales, internal climate variability could mask or confound kind of the response of SAI. And this is not new. This is, I mean, a good appreciation of internal climate variability and how it can dominate the forced response of climate change itself, to say nothing of SAI, has been pretty well understood for, I would say, a good decade, maybe more, maybe 2 decades, especially with Clara Desser's work. And so this is really building on some of that understanding, but then trying to lean into the fact that this is going to be, that we're not going to live in an ensemble mean. We're going to live in one world. Well, I should have set a clock to make sure that I stay on time. Okay. So this led us to design this this framing of potential for perceived failure. Again, probably a bunch of folks on the call today have seen this already, so I won't belabor the point too much. But you can think of both before and after SAI deployment that you could locally be experiencing warming or cooling. So in the decade leading up to a deployment scenario, you could be warming or cooling, and then following, you could be warming or cooling, or not warming is a better way to say it. And we labeled these quadrants in this way. So probably the most typical place that you would expect to be in a priori is something like a recovery scenario, where before SAI, your local conditions are warming, probably if you're on terrestrial surface on Earth. And then after SAI deployment, you would expect things to not stop warming, or at least to slow down in their warming. So something like this lower quadrant recovery. But in fact, you can experience warming before and warming after, or you can experience not warming and warming after. And so it's these two categories up here that could be perceived as a failure, where even though SAI might actually be working globally in the long term, it could be perceived locally over these shorter timescales, decadal timescales. It could be perceived as not working. And these decadal timescales are really consequential because these are time periods over which people form an understanding of what their local climate is. Now, there's lots of heterogeneity here in terms of perception of what constitutes a normal climate. There's lots of really cool social science happening in this space, particularly in the SAI world. And so this is evolving, but a decade is a useful benchmark for thinking of the way people kind of form an opinion about what constitutes something a departure from their norm. So anyway, so what we did is we classified the world in terms of this sort of potential for perceived failure framework, using the ARISE SAI ensemble to understand how frequently could people be in these two quadrants. And when I say people, I mean locations on the planet. And this is what that map looks like. So the red areas broadly correspond to areas where there are 4 out of 10 or more, so 40% or more probability that you could be experiencing these conditions of perceived failure. And so this process of going through this sort of, I don't know, thought exercise, but also then trying to walk through how natural variability could interact with over these shorter timescales, it made us think about this question of perception and how what role this might have in deployment scenarios and a decision to deploy SAI. And so that's where we sort of, so a backstory is that this whole idea of potential for perceived failure came out of a workshop exercise that we did here at CSU, where we wanted to understand what might motivate people to try and deploy SAI, specifically in the context of ecological tipping points. So trying to avoid the West Antarctic ice sheet from collapsing, for example, or try and cool off areas of the ocean where there's substantial harm to coral reefs, et cetera. So this whole idea stemmed from trying to understand what might people try and protect? How might they try and go about that? And that led to the perceived failure work. But then we wanted to pick that back up to say, okay, well, how could this change? How could perception affect the way people are thinking about deployment of unilateral SAI? So that's SAI where it's by a single actor or a small group of actors. And as a starting point, we were framing this as this is really led by Curtis Bell over at the U.S. Naval War College, treating SAI as a strategic decision. So not thinking about it as a kind of optimization decision about optimizing certain temperatures, but rather putting it starting from a geopolitical perspective of saying what types of strategic decisions might lead to a decision to deploy SAI. And so in that spirit, we used game theory to develop a formal model of how unilateral SAI could be initiated, and then how might another actor respond to that deployment. This is just a kind of a silly GIF to illustrate the idea that strategic decisions can be messy and kind of awkward. And so game theory is a way to formalize some of those assumptions to try and clarify and get rid of some of like the awkward arms over thing, to try and figure out how can we actually come to some understanding of the decision space that can emerge, albeit kind of in an idealized sort of way. So these are the assumptions for the game theory, the formal model that was developed for this work. We can actually argue about individual bullet points here, but this is what we used. And you could, if you used a different set of assumptions, you would end up with a different game, or at least different solutions for the game. And so I'll actually read these out. We understand the costs of UCI better than we understand the effects. This is UCI, unilateral climate intervention, sorry. UCI can have different effects in different places. An attempt to deploy UCI will reduce uncertainty about the effects of subsequent attempts. The impact of UCI on climate is temporary. Actors will know when others are deploying UCI, and actors might punish each other for deploying UCI. That might is important. So again, you could imagine adding additional assumptions or swapping some of these out, but this is what we used. And so this is the kind of like formalized representation of this climate intervention game, this two-player game. But it's simpler, I think, if I explain it in kind of a conceptual figure. So the first move, and I'm going to step through the different moves of the game and sort of explain the game theory logic about how it works. So the first move is the initiator, the one that's going to unilaterally initiate, decides whether to deploy a UCI. And they can either decide to deploy yes or no. And if it's no, then the game is over. Okay, so nobody deploys anything. And then in game theory terms, the phrase nature reveals is just sort of like what happens. So in this case, nature reveals whether the UCI outcome is good or bad for the initiator. And it can be a whole range. It could be the worst possible outcome for the initiator. So like, let's say I'm in the United States and it's really hot in Colorado and I want to deploy some SAI to cool it off in Colorado. But turns out, whoops, it made it way hotter. So that would be a bad outcome for me. But maybe it cools Colorado off perfectly. Great. It did what it's supposed to do. And that's the best outcome for me. So nature reveals. But then separately, the respondent, the second player in this game, decides how to react to the initiator's deployment. And so the second move, the respondent can either decide to punish or not punish the initiator. All right. And so the third move is what the initiator gets to decide to do. Nature revealed what happened to them, and then the respondent has decided to punish them or not. So they can decide to either continue doing it or not doing it. And so there's actually 4 outcomes that emerge from this third move, sorry. So if the initiator is punished, they can either stop, the punishment can be successful and they might stop deploying, or they could be undeterred and continue deploying. Or if the initiator is not punished, then that could mean that UCI is just tolerated. It just means that, yeah, the initiator can keep going. Or the outcome was still so bad for the initiator, even though they weren't punished, that they're just going to stop anyway. So in Colorado, like, again, to go to that little example, if it warms locally after I've tried to cool things off, I might just stop, even if I'm not punished, even if Wyoming says, yeah, we're not going to bother you. And so this is just an example of, this is an illustration of what the logic is for the game. And there's a paper on this, so you can just send me an email afterwards if you want to get a link to the paper that dives into the results. But really, one of the major consequential results for us was how important the a priori beliefs are, which means that the beliefs of the initiator before they've decided to do anything, about how confident they are that this will work for them. And so the bottom line, and so we don't need to, I'm not going to delve too much into the details here right now, but the bottom line is that if the initiator believes that the outcome would fall in a green area in this figure, which corresponds to either they're very optimistic for themselves, so they don't care what the respondent will do, or they're optimistic enough for themselves and optimistic about what the respondent will do. So those 3 conditions, if it's in that green area, then they're going to, UCI could occur. And so this led us to think that, okay, well, it is a substantial area of this decision space, which we didn't know from the outset what this would actually lead to. A substantial area actually leads to UCI happening, or at least being attempted. And so then this led us to ask the question, well, who could do it? Who might do this in our real world? We actually, I mean, it's in modeling land. So like I live a lot of the time just in modeling land, whether it be climate modeling or kind of social climate modeling or whatever. It's fun to play with idealized scenarios and sort of look at kind of idealized decision spaces. But we live in one world with a particular geopolitical configuration. And so it's worthwhile to go through, if we're going to go through this exercise, let's do it in the context of our kind of lived world. And there have been other people that have been doing this for years, honestly, especially including in the game theory space, but much more from like a coordinated multilateral type of evaluation. So in our approach, again, working with Curtis Bell, we were thinking through who might initiate. And to do this, we decided on a set of filters, essentially, where you start with all possible actors, which in this case, we're looking specifically at nation states. So again, we could talk in the question period about what other types of actors there could be. But for this work, we looked at nation states and we said, okay, so one of the filters, and one of the first filters is, do they have capacity? Can they pull this off, essentially? Do they have the resources, the funding? Do they have access to the right industries? Do they have the right geography, et cetera, to deploy in their sort of airspace or in airspaces to which they have access? A second filter is motivation. How badly do they need this? So are the conditions bad enough, temperature-wise, for the most part, that they might consider actually doing this? Because there are parts of the planet where a little bit of warming might actually be locally beneficial. And so part of the motivation was how badly, the motivation is how intolerable are their conditions. A third filter is confidence. How sure are they that this will be worth it? Now, this could be a couple of different things. One of them is just, do they have the geophysical confidence? Do they have confidence based on the best available science? Do they have confidence based on maybe their own experimentation using climate models, et cetera? But it could also be, do they have the confidence that they can get away with it domestically? Do they have the ability to control discourse publicly? Can they actually sustain a deployment for as long as they actually want to, given local conditions, whether that be kind of democratic flipping? So like in the United States, there's a tendency to flip between parties every few years. Do they think does the country think that they can actually do this for the period of time, probably a reasonable length of time, 10 or more years, if not much longer, that they would want to try and do this? Do they have the confidence they can pull it off? The fourth filter is insensitivity to punishment. So are they worried about how others might respond? So this could be, you can think of this as, are they relatively resistant or insulated from economic sanction? Are they able to resist others militarily, et cetera? And then ultimately, this can lead us to a possible initiator. So we did this for our real world. We applied these filters using a variety of different data on military expenditures, et cetera. And the long story short is we identified a number of different countries that met most of these criteria, happened to be in the Arabian Sea region. And you may recognize this region from other sort of either pop culture or past scenario efforts that you've come across in terms of explorations of unilateral deployment. India pops up a lot of the time. But in our group, we identified the Kingdom of Saudi Arabia as potentially the most a very possible unilateral initiator. There's a whole variety of reasons for this. It has some of the fastest growing, some of the hottest temperatures, not just fastest growing, but some of the hottest temperatures on the planet. And those are going up faster than the global average. It's an oil exporting state. Most of its economy, at least for now, is still reliant on fossil fuel extraction. As recently as a few years ago, they actually hosted a summit, which was how can climate change be addressed without reducing global dependence on oil. And so and they've been one of the handful of countries that has gone on the record of resisting global governance approaches to SAI, or even kind of broaching the topic. Other factors are that it's the fifth ranked spender on military spending. This was a pretty substantial filter. Most of the countries in the world dropped out at this filter. This was one of the first filters. It has a growing aerospace sector. So there's the Saudi Aerospace Company, and then the Saudi Arabian Military Industries, which is a much larger state-owned enterprise, which is leading the charge on a lot of its military aerospace activity. And then lastly, this is just one really sad example, but it's fairly insensitive to kind of international opprobrium. So it's insulated from many countries being dissatisfied with what they're doing. And so all of this sort of conspired to say, well, let's explore what would happen if Saudi Arabia were to do this. What would that look like? How could this unfold? And so to do this, we actually just borrowed a lot of the ideas from so Wake Smith has done a tremendous amount of work in this field, trying to figure out a lot of the engineering details, the actual kind of workflows, the technical requirements that would be required to, I should say Wake Smith and a lot of his colleagues, the technical requirements that would be required to actually deploy SAI. And so we built a scenario kind of on the scaffold of a lot of that work to say, what would it look like if Saudi Arabia was just trying to cool in its airspace or its adjacent airspace, and do a kind of a typical ramp-up scenario, pretty similar in ways to the ramp-up scenarios that are used in, say, the ARISE SAI set of simulations. So what we wanted to do is we said, let's bake this together. Let's not just talk about having these things be separate. Let's take this unilateral initiation scenario as it's represented in the game, or as supported by the game theory, and then simulate that scenario and see what happens. Explore how the climate evolves under this very specific storyline, you could say, and then explore which respondents might come into play and how could we explore this? This was actually really hard to do, not just because like climate models are complex and so forth. We have the expertise in our groups to actually run CESM, to make the changes to the controller algorithm, et cetera, to tinker with that. But to actually figure out how to implement these different scenarios in a way that was trying to be as close to realistic as possible in the sense of the location of deployment, et cetera. And then how would we interpret the results from a model to tell us something about the state of the climate? So it was sort of putting ourselves in the shoes of these potential people that would be trying to understand and perceive what was unfolding in the climate system. So again, this is, and I should say this is unpublished. It's submitted for publication, but it's unpublished. So please don't distribute this right now. Although I guess you're recording this and it's going to go on YouTube. So just cite the work. It's a preprint right now. And so what we did is we took this this scenario, represented it using the game theory, had Saudi Arabia deploying in the Arabian Sea, and then represented it in CESM2, and we actually did 10 simulations of the Saudi Arabian scenario, and we explored the climate evolution. What we wanted to do is, because we were deliberately interested in understanding and really exploring this game theory logic, we wanted to identify, is there an ensemble member where Saudi Arabia's temperatures roughly stabilize? And for the most part, well, we don't know for sure because we would need to have a much larger ensemble to say this with confidence, but it's probably just internal climate variability that Saudi Arabia's climate cooled. It's probably not the SAI deployment. It's probably some other, or it's a combination of factors rather. But we identified the scenario where it works in Saudi Arabia, and then we wanted to understand, well, who would react based on it working, air quotes, in Saudi Arabia. And then we did this exercise, and the first time we did this iteration, we identified that China could perceive that it was working in Saudi Arabia's airspace, or Saudi Arabia, the geography of Saudi Arabia. And China, in this particular ensemble, China's temperatures were very high, and the respondent in this case is China saying, look, it was so high, and rather than punishing Saudi Arabia, we're going to do a complementary deployment. So instead of actually punishment, it's tolerated, and then they do a complementary deployment. We did another simulation to explore the climate evolution of that. We did the same thing with the United States, actually, as a respondent in the next case, doing, again, a complementary deployment. This is part of the fact that Saudi Arabia is difficult to punish. And many large countries, including the United States and China, are substantial allies of Saudi Arabia, economically, militarily. The United States has a much longer relationship with Saudi Arabia than China does, but in recent years, especially with the Belt and Road Initiative, China has been building very strong ties with Saudi Arabia. So, zooming out, and then I'll stop because I wanted to leave some time for questions. The three take-homes. Unilateral initiation of SI is still a very reasonable possibility worth exploring, and that's with a primary result from that sequence of work on the game theory. Another main point that I think is critical for this community to keep grappling with is that internal climate variability is essential for considering plausible deployment scenarios, and not just the deployment itself, but the ongoing deployment and how that deployment could be sustained. This is also true of just kind of the climate change community in general, but this is something that I think from a scenario perspective, we really need to lean hard into. How can we include internal climate variability in all of this work that we're trying to do in a realistic way, but also acknowledging that we can't explore every single ensemble member. And I would argue that this is only scratching the surface. I think there's a huge world that's going to open up in the next few years, especially kind of building in that comment from the previous talk, with the kind of advent of emulators, reliable emulators, that you can actually explore relatively quickly many different types of scenarios. Oh, that's my time. Okay, so I will just leave this slide up here as the summary, and then please feel free to reach out if you have any questions.
Thank you very much, Pat. That was great. Very interesting talk. Does anyone have questions? I guess I could. Yeah. Kwesi?
Yeah.
Do you want to unmute?
Yes, thank you. Thanks, Patrick, for your wonderful presentation. I really enjoyed it. But my question is, when it comes to something like stratospheric aerosol injection, as a climate modeler, we typically think of it as a global sort of decision making that has to be made. And when you look at us modeling, we do this over these latitudes that we talk of 15 north, 15 south, 30 north, 30 south. We do our sort of surface injection at these latitudes. And from what I'm understanding from your presentation, you did mention that some states could take the initiative to do it. And I don't know how that is going to be possible. Is it just that it could be any sort of climate intervention, or you're looking at these large-scale climate interventions that we model? Thank you. I would appreciate a comment on that.
Yeah, just so I'm going to pop up this extra slide. So to answer that question, this is what the some of the scenarios look like in sort of the baseline situation, where right here you can see this is where and this is what I was referring to, is like kind of tinkering with the the controller so that it's actually only deploying at this particular location on the planet that Saudi Arabia has access to, and that so we're deliberately exploring a new simulation. So we're using a lot of the existing structure of the Arise kind of setup for CESM. And then we're sort of just tinkering with it a little bit to make sure that it can simulate precisely the type of scenario that we want. And so, and just to zoom out just a touch from your question, I think our group in general is really interested in exploring these non-optimized, non-optimal scenarios. Not to say that those aren't valuable, because they are really important, especially just to understand the global climate response. But that there's a lot more types of scenarios that are possible out there that are still ought to be explored to understand what the consequences could be geophysically, but also how might these consequences be perceived. That's an area, a topic, a part of this research community that still has, I think, a lot of important room to grow.
Greg?
Oh, thank you. It was a very interesting talk. Just seemed to me after listening that if you're a country that's a democracy and the leadership, the elites want to deploy SAI, then the best way to do it is to convince a totalitarian state such as Saudi Arabia to unilaterally do it at small scale. That gives you permission to do it, as you sort of implied. Yeah, it's been done, but it's now a thing. Let's do it. So you can do it globally once the instigator has sort of made it a thing. How about that?
Yeah, and I think this is a really, it's a great point, and I think it's an important point that not every deployment scenario is going to be, needs to be a deliberate long-term investment or in a strategy that's going to be sustained for decades. It could be a provocation to gain a seat at the table. So maybe you don't actually have the resources to sustain something for 50, 100, 200 years, depending on the scenario of SAI deployment. But you have enough to do it for 2. And you have enough to at least get everybody's attention and sort of force everybody's hand. So there's both, like you gave an example of a situation where a certain type of government might try and get another type of government to do this more or less for them. Or you could have a type of government that's just going to do this to say, hey, this is a huge problem. We're going to kind of force the question by doing this on a scale that's big enough. So not to make sunsets, people, but doing this at a scale that's actually going to affect persistently in a multi-year sense the climate, such that you have to now have a conversation that people weren't willing to have or weren't ready to have yet. So I think that is another huge area of this kind of research that could be explored in the near term. And again, that's also where emulators are going to come in really handy. If we have good enough emulators that can capture natural variability, then this is an opportunity to really explore the whole kind of buffet of scenario possibilities.
Right, thank you. It's a bootstrap process in that sense.
Yang?
Hi, thank you for the talk. Yeah, I might have missed something obvious. You seem to imply that the unilateral deployment, say from Saudi, they can specifically benefit their local country's climate. And in response to some side effects in other countries, other countries can also deploy their own schemes to balance the climate for their specific country. I thought SAI is more globally deployment, and you really don't have much control of where will benefit and where will actually suffer more. Can you?
100%. Yeah, this is not to say that this is somehow going to actually be effective in cooling their local geography. The point here is that a decision to deploy, is, at least based on our research, would only partly, and perhaps very partly, be driven by the best scientific research out there. It's going to be driven by a lot more than that. And so this research is actually giving credit, or sort of it's paying attention to the other parts that will go into that decision, the strategic aspects of that decision that are in some ways totally independent of the outcome, but are much more focused on what does this country want, what do its citizens demand of its government to actually do, and the government might say, yeah, this isn't going to work, but our citizens want us to do this, and so we're going to actually deploy SAI. It's going to get the goodwill of our citizens that we want. And then, the consequences might not be what we want, but we're going to, at least in the short term, be responsive in the way that a government tends to be, which is providing that the citizens have any power over what the government decides to do. It might not be in the best interest of the country or the planet. And so I think that's acknowledging that is another thing where, especially like working with other disciplines like political science, economics, other branches of social science, is essential to see this topic with greater clarity about how these scenarios might actually unfold in practice. Sort of echoes a little bit what Lili said, just that we need to have many other different types of communities at the table when we're thinking about these questions than maybe the conventional folks.
So if you don't mind, I'll ask one last question. I was wondering if you explored scenarios where you actually like bring the temperature down. So I think in these scenarios you're talking about, you're like stabilizing the temperature, if I'm looking at the panel F correctly. And I'm just thinking like, if we do deploy, like if Saudi Arabia says, okay, actually we want to deploy, they might say, well, it's too hot now. So our target is actually going to bring the temperature down. And so then everything you're talking about, the potential for perceived failure, might actually be less of an issue if you like the distance between the sort of, if the SAI forcing is quite large, right? So yeah. Oh, I think you muted yourself.
I did. Yeah, that's an interesting point. And this gets to a challenge of, so what we did here is like it's not a one-off simulation, because we actually simulated Saudi Arabia's deployment, or I should say the Arabian Sea deployment. You could actually swap in any number of countries from the geophysical side that have access to that spot. And so we did 10 ensemble members. And so across that set of ensembles, you could explore the perceived failure question, which we haven't done yet. That's a really interesting point. But if I understand correctly, you could explore, are you trying to say that you could explore different deliberate, almost like structure it so that it's achieving a perceived outcome? Is that what you mean?
No, or just simply saying you could increase the amount of aerosols you put in the stratosphere so that your target is not just to maintain the temperature at where it is when you start deployment, but to actually bring it down.
Yeah.
The idea being
I
the
see.
storyline is like, oh, Saudi Arabia is now too hot. So actually you want to bring the temperature down rather than just...
Right, I see what you mean. Yeah, you could do that. And I guess the challenge is, not a challenge, but unless you do it like you hit it with a big hammer, like you deploy a lot of aerosols, you'd have to do it for longer, right, to get to that cooling result, the idealized cooling result, theoretical maybe. And so that's another question of, we're trying to walk this line of trying to be plausible, at the same time exploring possibilities that are currently not deemed plausible. So we're outside the range of what is considered maybe plausible right now, but still trying to stay within that little boundary. And part of that goes back to how long could a country actually sustain this by themselves without other countries really stepping in, or the global community stepping in? I don't know the answer to that. That's another reason to explore potentially some of those scenarios. I like that point, though. That's a good point of where you could actually have the scenario be designed to, I guess it's a question of, you would just have to have the ramp up a lot steeper, or do it for a much longer period of time to see reasonably see a result.
Yeah. Okay.
Okay.
I think we'll stop there. Thank you very much for a great talk.
Yeah,
thank
you bet.
everyone.
Thanks.
If anyone else wants to give a talk, please reach out to me or Symposium. So yeah, thanks very much.
Thank you.